Hello everyone, this is 47th lecture of the course Process Equipment Design and I welcome you all in this lecture, and here we are going to discuss design of PEG column with the help of some examples. Okay. So, if you remember the last week where we have discussed design of PEG column, and in that we have computed height of the pegged bed as well as diameter of the PEG column. Okay. And here we are illustrating the design of PEG column through some example. So, let us start with the example 1. So, in this example 45 kg per hour of air and sulfur dioxide mixture which contains 10% SO2 is fed to the pegged column, and that is specifically as absorption column. 96% of SO2 is absorbed by the water in this column. So, what is the remaining percentage of SO2 in the air and SO2 mixture? That should be 4%, right. So, the operating pressure of the column is 1 atmosphere and temperature of water and gas mixture is 25 degrees Celsius. 38 burl ceramic saddles are used as a packing material. The recommended pressure drop across the packing is 21 of water per of packing. Fine. And along with these, some physical properties are also given, such as dl, that is diffusivity in liquid phase, and dV is the diffusivity in gas phase. Okay. So, because gas is easily diffusive, so its value is lesser than the diffusivity of liquid. Further, we have physical properties like mu v, that is the viscosity of the vapor, viscosity of the liquid, density of the liquid, density of the vapor, and here we are given Lm, and that is liquid mass flow rate, and that value is around 90,000 kg per hour, and m value is given as 23, which is the slope of the equilibrium line, and what we have to estimate are number of transfer units, column diameter, height of transfer unit and column height. Okay. So, in this way we can. So, this is the example which we have to solve, where design of PEG column is considered, where height as well as diameter of the PEG column are to be computed, and in this example we will consider Cornell's method for design of PEG column. So, let us start the calculation of this. So, as far as height of the PEG column is concerned, that is basically HOG as well as NOG. So, first of all we will find out NOG and then we will proceed for HOG calculation. So, NOG, if you consider, that depends on initial and final concentration of the solute in gas phase, right. So, if we consider the initial concentration of sulfur dioxide in gas phase, so that is given as 10%. Okay. So, that value I am considering as 1%. So, that value I am considering as 0.1. Okay. And Y2 is the concentration of the solute at exit condition, and here because 96% is dissolved in the water, so 4% is available. So, 4% of 0.1. So, that should be 0.004, right. So, in this way you can find Y1 as well as Y2, and next we have to find out Gm and Lm value, and these Gm and Lm are basically molar flow rate, not mass flow rate. Okay. And if you consider, in this example we are given the mass flow rate of the gas mixture as well as liquid stream, and that is water. Okay. So, mass flow rate is given as 4500 kg per hour, and to convert that into molar flow rate, we will consider the molecular weight of the air, because it has 10% of SO2. So, molecular weight of air will dominate. Okay. So, I am considering 4500 kg per hour as the mass flow rate of the vapor stream, as the mass flow rate of the gas stream divided by 29, that is the mole, divided by 29, that is the molecular weight of the air. So, molar flow rate of gas you can find as 155.17 kilomole per hour. Okay. In the similar line, I can find the molar flow rate of liquid stream, and that is water. So, here you consider 90,000, it is not 9,000, 90,000 is given to us, and that should be divided by 18. So, 5,000 kg, so 5,000 kilomole per hour of water is available. Okay. So, now we have all values to find out energy. So, if you focus on the expression of the energy, it is like this, where m is given as 23, gm and lm values I have already calculated, y1 and y2 you know already. So, considering this expression I can find, so considering this expression I can put the values of all parameters into this, and it is shown over here. And when I solve this equation, we can find energy value as 7.2, right. So, this is basically number of transfer unit, and it is, so this is basically number of transfer unit. Okay. Next we have to find out HOG value, that is height of the transfer unit, and if you recall the Cornell's correlation, in that case we have NOG which is dependent on the diameter of the column as well as height of the column, right. So, first of all we will compute diameter of the column, and then we will proceed for HOG calculation. So, as far as diameter of the column is concerned, this is the expression for which, this is the expression, and based on that we can calculate VW, and here it should be star because it is per unit area value, right. So, we have to find out K4 value first, okay, and then we can find out VW star, okay. And K4 value is basically dependent on the FLV value, and this is the expression of FLV. Here you consider LW star as well as VW star, and these both are based on per unit area value, right. So, area will be cancelled out from 2, and then we can simply represent as, and then we can simply represent this as LW by VW, that is the mass flow rate, fine. So, considering these values, so considering these value we can find out FLV value which is coming out as 0.6957, okay. Rho V, rho L, all these values are given to us, and please consider here 90,000, not 9,000, right. So, next we have, so once I am having the FLV value, I need to find out K4 value through the graph, and you see this is the graph, okay. And in this example you see the pressure drop is given as 21 mm of water per meter of packed height, right. So, we have to use this curve, and as far as FLV value is concerned, it is coming around 0.7, right. So, that will be somewhere here, okay. So, when we consider this point, we can find out value of K4, and that should be like this, okay. When you draw the straight line, you can find the exact value, and the value comes as 0.37 if you read the graph properly, fine. And if I focus on this equation further, I have found, and if I focus on this equation further, I have found out K4 value, and next we have to find out FP, that is the packing factor, and here we have the table of the packings, and if you see, we are given 38 mm burl saddle, okay, because burl saddle is not available in this table, that will be close to the intellect saddle, and we can use this packing instead of burl saddle. However, some difference is there, but more or less it is falling in the same category, right. So, here I am having 38 mm size, and corresponding to this FP value you can find out as 170. So, here you can see FP value we are taken as 170. Okay. So, considering K4, Fp and all others and all other properties, we can find out VW star value, which is coming out as 0.894 kg per meter square second, right. And further you are given with the mass flow rate of the gas, and that is 4500 kg per hour. So, that we can consider. So, this we can divide by this VW star, and this is basically 4500 by 3600 as it is considered in per second, and we are given VW star value as this. So, 1.3982 meter square is the column diameter, and 1.3982 meter square is the column cross section area, and considering that, you can find out column diameter as 1.334, right. So, in this way we can find out the column diameter. Now, next we have to find out the value of HOG, and HOG will depend on the diameter as well as Z value, right, and Z value will depend on HOG into NOG, fine. Till now only NOG you have obtained, but HOG you need to obtain, and for that you have to consider Z value. So, that will be an iterative method, right. So, first of all we will assume the value of Z, and then we will proceed to find out the value of Hg as well as HL. So, how we should consider the value of Z? Initially Z value we will consider based on assumption of HOG, right, because NOG value I have already calculated. So, HOG value initially I am considering as 1 meter, right. So, initial assumption is HOG is equal to 1. So, once I am having this, we can find out Z value as 7.2, because 7.2 is the NOG and 1 HOG value I have considered. And so, if you consider HL correlation, here I need K3 and phi h. Okay. Along with this, psi h is also required, which is for the calculation of Hg over here, okay, that we will see in the next slide. But find out the values of K3, phi h and psi h, and for that I need percent flooding. Okay. So, how I can find out the percent flooding? 0.37 is the K4 value, which we have seen in the last slide, and how this value 0.87 comes. Okay. So, to find out K4 we have to see this figure, and if you see here I am having FLV value which is equal to 0.7, and when we have drawn the line upward, we can find the value of K4 at operating condition here, and if I further extend this line up to flooding condition, I can find K4 value at flooding condition like this, right. So, in this way you can find out the K4 value at flooding condition, and it will come out as 0.87. So, considering this, we can find out flooding as 65%, which should be less than 85%. Okay. Now, at this 65%, we have to find out value of psi h, K3 and phi h, and for that we can consider the graphs like this. Here we can read the value of K3 corresponding to 65% flooding condition. So, that should be somewhere here, and you can read the value. Okay. So, if you read the value properly, it is coming out as 0.77, right, and further we can find out value of phi h, So, here you see we have flooding condition around 65%, and when we draw the line upward, you can see we can have the packing as 38 mm Burl saddle, and here if you see asymptotic line is falling and it will be extended further. So, we can consider the value as 80, right. And for phi h value, we have to find out LW star, and that LW star you can calculate considering liquid flow rate, and that should be 90,000 divided by 3600 and divided by the cross sectional area. Okay. So, its value comes as 17.88. So, when we consider this graph, 17.88 will lie somewhere here, and we can consider value of psi h. We can consider value of phi h at this point, and its value should come as 0.095 when you read the value from here. Okay. So, in this way we can find out the value of different factors, and once you have these factors we can find out the Schmidt number for liquid condition as well as vapor condition, because vapor condition will be used to find out value of Hg. So, we will do the calculation together. So, here we have the Schmidt number for vapor, and this is the expression, all properties are given. So, we can find the value of Schmidt number at vapor as 0.8264, right. Schmidt number for liquid condition we can find value of 555.55, and Z value we have already seen, it is 7.2. So, considering all these value we can find HL value from this expression, and its value should come as 0.598. Okay. All values you can put in the given expression, right. And next we have to find out Hg value. Okay. And this is the expression of Hg, where this DC expression I have to see first, because in this example diameter is more than 0.6 meter. Okay. So, we will replace this whole expression with 2.3, right, and because solvent is water only. So, we will consider F1, F2, F3 value should be equal to 1. Okay. So, other parameters you have already calculated, Z you know, and when we put the values in Hg expression, in this way we can find the Hg value as 0.5775, right. So, we can find out HOG based on Hg as well as HL value, and considering mgm by Lm. So, considering all these value we can find out HOG value as 1.0043. So, that will be close to the assumption which is 1, right. So, I consider that assumption is correct, and so I can find out the Z value as HOG into NOG. Now, I will put correct value of HOG, and the height we can obtain as 7.23096, right. So, in this way we can find out the height as well as diameter of the pack column. Now, if in this case HOG is not close to the assumed value, okay. So, what we have to do? We have to do like whatever calculated HOG we have obtained, based on that we will further calculate Z value, right, because NOG has the fixed value. So, in this way, considering revised value of HOG, we will calculate Z, then HG and HL, and then HOG, and then Z value. So, this we keep on doing till 2 consecutive iterations have 0 value difference. Okay. So, that should be almost 0, as here we can see that we have considered 1 meter and we have obtained 1.0043 value, right. So, in this way we consider the design of pack column, and further we will see few more examples to illustrate the design of this column. So, let us focus on example 2, and this example I will cover quickly because details I have already explained in previous example. So, here I am having second example. In this, ammonia and air mixture is entering to the pack column to absorb ammonia in the water. Feed enters at 1.5 kg per second, where ammonia has mole fraction of 0.15, right. At the outlet 0.0015 mole fraction of ammonia is left in the gas stream. Water which is available as 2 kg per second, and that will be used as a solvent in the column. I need some data which are given as I need some data which are given here as molecular weight of ammonia and air are given. Burl saddle packing is used with 25 size. Pressure drop in the column is 42 water per meter of packing, and that is available at 25 degree Celsius. Property at the operating temperatures are given like this, okay, because water is there. So, F1, F2 and F3 should be considered as 1 and this should be used in Hg calculation. Okay. So, here again I am considering Cornell's expression to find out Hg as well as HL, right. So, you see the flow rate of gas stream, that is ammonia and air, is given as 1.5, water flow rate 2, and here we have Y1 and Y2 values and mgm by Lm. So, here I am having Y1 and Y2 values and I can simply find out Y1 divided by Y2. So, first of all I have to find out NOG value, and for that we should consider mgm by Lm, right. So, in this case if you see, we do not know the, so in this case you see we are given Gm as well as Lm value. Actually mass flow rate is given, but that we can consider in molar flow rate, that is not the problem, but I am not given M value. So, I cannot calculate mgm by Lm. So, if you remember the design of pack column, there if mgm by Lm value is not given, we consider the optimum value, and that optimum value is 0.8. So, that we can consider over here. Y1 and Y2 we can obtain as Y1 by Y2 we can obtain as 100, and so we can see the value of NOG from the graph. Okay. So, that would be Y1 by Y2 and that is 100, and here I am having the value as mgm by Lm 0.8, right. So, this value we can consider as NOG value. If we consider 100 Y1 by Y2, so value will come as 15.2 from the graph if you see it carefully. Okay. So, pressure drop is given as 42, all parameters are given like this. So, next we have to find out the column diameter, and for that we should see the value of K4 from the graph, and for that I should know FLV value which we can calculate from this, right. So, once I am having the FLV value which is equal to 0.16, somewhere here it will lie, and 42 is the value. So, we can consider this plot and we can draw the line like this. So, K4 value we can obtain as 0. So, K4 value we can obtain as 1.2. When we extrapolate this to flooding line, this should be K4 at the flooding condition, and that should be 2.75 if you see it carefully. So, around 66% flooding is there. FP value we can consider as 300. FP value we can consider as 300 from this table corresponding to 25 size, right. In this way we can obtain the value, and we can further calculate VW star, okay, and that value we can obtain as 4.238 kg per meter square second, and so we can calculate the column diameter which is again coming more than 0.6 m. Okay. So, this we have to consider in Hg calculation using Cornell's method. So, here I am having the equations for the Cornell's method. So, Schmidt number for vapor and liquid condition we can calculate as we have discussed in the previous example. LW star we can find because mass flow rate of liquid is given to us. Initially I am assuming HOG value as 1, NOG we can obtain as 15.2. So, Z value should be 15.2 only. This is phi, psi and K3 values from these graphs. Okay. These graphs I have already explained in the last example. So, I am not going into detail of that. So, considering this we can find out HL value as well as HG value. So, here again this you should replace by 2.3 and Z is 15.2. So, considering all these value we can find HL and HG, and through this HOG calculation can be considered, and the value of HOG should come as 0.5595, right. So you see, initially I have assumed HOG as 1, and now I have obtained just half value of that. So that will not be acceptable. So considering this HOG, we can find out Z by multiplying this with 15.2 NOG, and phi, psi and K3 values will be same, and further we can find out HOG and further I can find out revised value of HOG as 0.49. Still it is differ than the previous value. Okay. So I keep on doing the iterations like this. You see, 0.49 we have assumed, we have obtained 0.478. Further this value we have assumed and find out 0.475, and considering this value over here we can find out 4746, and further considering this value we can find out 46, and further considering this value we can find out HOG value as 4745, right. So we can consider that it is pretty close to the assumed value, and so 7.2 meter will be the total height of the pack column. Okay. So in this way we can consider the solution of this example. Now here I am having third example, and I will cover that quickly because I have to tell a different point over here. Okay. So in this example, gas A is available in air and that should be absorbed in the water. Feed is 1.2 kg per second, 0.1 is the mole fraction of gas A. At exit this much mole fraction is there, and exit water stream contains this much mole fraction of gas A, right. And here we are having the properties where gas A and air molecular weight are given, packing 25 mm. So you can consider pressure drop as 8 mm water per meter of packing, right. So here you see we have different parameters, and here I have to, and in this example m value is given to us, that is 14. Okay. So you see here molecular weight of A and air. So you see here we are given molecular weight of A and air. So average molecular weight I can find out, that is 0.1 into 20 plus 90% air. So that should be multiplied by 0. So that should be multiplied by 29. This I have not considered in example 1. Okay. So that you can see, and here I am having the gas molar flow rate as this, and I do not know the liquid molar flow rate, right. So I can obtain that by making the balancing. I am considering that initially water has 0 gas A. Okay. So by making the balance over here we can find out LM value, and that should be 1.40325, because X2, or we can say the final concentration of gas A in liquid is given as 0.003. Okay. So mgm by Lm we can find out, and then we can find out NOG value considering this expression, and here all calculations are repeated, and we can find out diameter of the column as 1.1655. Okay. And considering Hg, HL value and HOG value, we can find out HOG value as 0.422 and 1 value we have assumed. Okay. All these value you can see on your own, and we can see that sufficient error is there, and further we can consider this HOG, and now the Z value you can obtain as 2.97, right, multiplying HOG with NOG. So here you see Z value is coming less than 3 meter. Okay. And if this is the condition, we consider Hg value as well as HL value considering this factor as 1. Right. So, this change you have to do, rest calculations are same. So, you can find out final diameter of, so you can find out final height of the column as 2.53 meter. Okay. So, in this way we have considered different example. These are the references, and here I have the summary of this video that design of pack column is illustrated with examples. 3 different examples are discussed, use of all graphs and tables are described in detail, and that is all for now. Thank you.